Section 2.6, we're going to look at forced motion. And as part of forced motion, we'll talk about something called resonance. So you might remember back a few sections ago, we talked about having undamped, unforced motion. So this would be undamped, unforced. Why is it undamped? No, that would be unforced. It's unforced because that's a zero there. If there were a number here or a function here, this would be forced. Why is it undamped? There isn't the third thing in the middle. All right, so damped motion, you might remember. Damped motion looked like that. So this one would be unforced because we still have zero over there, but this one would be damped because we have that term. This one is unforced and undamped. All right, so let's talk about undamped but forced motion. So forced motion would mean we have some sort of function over there. Now typically this function over here is going to be a trig function involving sine or cosine. I don't know what to call it. Bx. I don't really want to use b. Usually the force will be a function involving sine or cosine. How come? Because the spring is bouncing back and forth, it's oscillating. Typically we want our force to be something that keeps the thing oscillating. What if our force was just like a constant, or what if it was just a polynomial? What would happen? Like what if our force was just 3 newtons? It's a nice constant. What would happen to the spring?
It would just go down.
It would just stop because you'd just be pushing it in one direction. So you would be forcing it, but you would push it, and eventually it would stop. It would stop almost immediately, in fact. So that's why typically our force function is going to be something which oscillates, because what we really want to do is we want to keep the spring moving. Okay. When we had mx double prime plus kx equals 0, what kind of solution did we get? What was our complementary solution? You don't have to tell me the whole answer, just what did it look like? What kind of function did it have? Not quadratic. You have mr squared plus k equals 0, where m and k are both positive numbers. So what kind of answers did you get to that characteristic polynomial?
Imaginary.
You got imaginary answers, which told us our answer had sine and cosine. But then we did a whole bunch of fancy trigonometry, and we wrote it as one cosine function, didn't we? So this turned out to look like c times cosine of, I think we used omega naught x minus alpha, I think is the way we wrote it. Where you might remember that omega naught was the square root of k over m. Okay, so that's what our complementary solution looked like. So typically what's going to happen, we're going to have to find our particular solution. We're going to have mx double prime plus kx equals, most of the time here, our force function is something that involves a cosine. It could just as well be a sine, but typically we use cosine. Why do we typically use cosine? It doesn't start at 0, that's true, that's not really that important.
It represents x or
If I could use sine and have x in there just as well.
It breaks down to the cosine parentheses a plus b.
Nah,
Isn't it because when you start your oscillation, you start at some maximum or not at equilibrium?
not necessarily. You might start at equilibrium and just give the spring a slap and have it start moving. Right?
Yeah.
Does it get rid of the function?
No. I think the only reason we use cosine here is because we had cosine there.
Oh.
We're going to make our functions match, that's all. You guys are all thinking way too hard. That's why we use cosine here, because we ended up with a solution cosine there. All right, so if I have this as my equation, what would I guess for my particular solution? A cosine omega x plus b sine omega x. All right, so I'm going to take that. I'm going to find the first derivative. I'm going to find the second derivative. I'm going to plug it all in, and I'm going to figure out what the values for a and b have to be. All right, so x p prime is going to be negative a omega sine omega x plus b omega cosine omega x. Second derivative, xp double prime, is negative a omega squared cosine omega x plus, I should have written a minus, negative b omega squared sine omega x. All right, looks ugly, but turns out it's not going to be so bad. Plug in for my second derivative. I'm going to have negative m a omega squared cosine omega x minus m b omega squared sine omega x plus k times my original function, k a cosine omega x plus k b sine omega x, and all that stuff all added together has to equal this lowly little cosine omega x here. Then we equate, that's right. So we combine all the things that have cosines. Here's one that has a cosine, and here's one that has a cosine. That tells me that minus m a omega squared plus k a has to equal 1. And then let's do the other one. We equate all the sines together. So we've got sines and sines. So that equation is minus mb omega squared plus kb equals 0. And I should have told you one important thing way back from the beginning. I want to make sure that omega is not the same as this omega naught. Why do I want to ensure that this omega that I'm using here is not the same as that omega naught that I got from there? What if they were the same?
It would mess something up.
Then this would no longer be linearly independent, and I'd have to multiply it by x, and it would get a lot uglier, wouldn't it?
Wait, why did you put a J in front of the...
That's not a J, that's supposed to be a semicolon.
Oh.
It did look like a J, I agree. That's a semicolon. Okay, so now looking at these two equations. How can you solve, let's do this one. How do you solve this equation? Which letter are we trying to get along? We got M, we got B, we got omega, we got K, we got B. Which letter are we trying to get all by itself?
B.
Trying to get B all by itself, right? Because we're trying to find B and A.
Well, B and A, there isn't a B or an A in either. Those coefficients are related only to one equation.
Yeah, it turned out that we only got A's in one equation and we only got B's in the other equation. So we really don't have a system of equations, we really have two distinct equations.
So there's going to be both equivalent to M's and omegas?
Yes, except for this one. What's B?
0.
B has to be 0, how come?
Because everything 0 divided by all that extra stuff.
You can factor out the B and divide by all that other stuff, and you get B is 0. Which means in my particular solution, I really don't have that. My particular solution is only going to have a cosine in it. That's nice, isn't it? So do you see what I mean when I said we're going to make this solution match that solution? We're going to have cosines in both solutions.
So that doesn't always happen. Should we still guess that it has the B sign and then go through and then if we get a 0 for B, there it is?
Yes.
Okay.
But a better question is, when will it happen?
When will it happen?
Huh?
When will it happen?
When will it happen?
When we have a damping effect, correct?
When you have an x double prime and an x, but no x prime.
When we have damping is when we get a first derivative, when we actually switch the coefficients around with the sines and cosines, otherwise everything matches.
Correct. So, when you have just the x double prime and just the x, then your particular solution is only going to need a cosine, or you could have used just a sine. Either one of them would have worked. But one of them is going to drop out. All right, so for the second one, I can factor out the a and then divide. So this is a times minus m omega squared plus k equals 1. So a is 1 divided by negative m omega squared plus k. And then I'm going to do something a little bit unusual, something that's going to surprise you at first, but I'll tell you why I'm doing it in just a minute. I'm going to take this fraction, and I'm going to multiply top and bottom by 1 over m. So that gives me up on top 1 over m divided by omega squared, negative omega squared plus k over m. The reason I divided top and bottom by k over m, or divided by top and bottom by m, k over m is something important. That's omega naught squared. So this turns out to be 1 over m divided by negative omega squared plus omega naught squared. So what I want you to consider is what's going to happen when this omega naught squared and this omega squared are close to each other. You're going to get something that's close to 0 on the bottom. What happens when you get something close to 0 on the bottom to the whole fraction? It gets really, really big. And this is our number a. A, back up here, is the amplitude of that function, isn't it? So when omega naught and omega are close, whatever close means, how close do you want them, amplitude gets very big.
So that keeps the resonance in the material.
And that's where resonance comes in. That's right. When omega naught gets close to omega, you're going to get a very, very large amplitude, and that's what we call resonance. Basically, what's happening is the solution you get from the complementary function and the solution you get from the particular function are linearly independent, but barely. They're very, very close to each other. So this force function is acting together with this complementary solution, and it makes the wave continue to get bigger and bigger and bigger. And what happens when waves get bigger and bigger and bigger? Things break. Tsunamis happen, things break is the important thing. Now, what happens when you have forced damped motion? And again, our force is typically going to be an oscillating force, typically going to be cosine. What did we discover about the complementary solution? Well, when we talked about this, when we set this equal to 0, we discovered that three things could happen. Because you end up solving a quadratic equation. When you solve the quadratic equations, you got three possibilities. You might get two real roots. What happens if we get two real roots? What kind of equation is this complementary going to have?
Overdamping?
It's overdamping. I'm just looking for the formula that we ended up with. It's going to end up with, we had three possibilities. We could have a C1 e to the negative R1x plus C2 e to the negative R2x. If we get two real solutions, both the real solutions were going to be negative, and when x, not x, this is t here. And when t gets big, this very quickly gets close to 0. So that was one possibility. What if we got a repeated root? One root, but it was repeated.
So C1 and C2x.
We would have a C1 e to the minus R1t plus a C2t e to the minus R1t. But once again, what's going to happen when t gets big? When t gets big, this function is going to get close to 0 because we have these negative exponents again. Or the third possibility was that we ended up with two complex solutions. So the third possibility is the equation might look like e to the minus RT times C1 cosine, I need a letter, AT plus C2 sine AT. And once again, what's going to happen when t gets big? It goes to 0 because you've got this e thing. So in any case, your complementary solution, as t gets large, is going to go away, isn't it? It's going to get close to 0. All right, so instead of complementary, this solution is usually called x sub tr, where tr stands for transient. And what does the word transient mean? What does the word transient mean in English? Forget about math.
Going through?
Something that goes away, usually. A transient person is somebody who comes and leaves. A transient solution in mathematics is one that goes away. It gets close to 0. So in a sense, this complementary solution really doesn't matter. Because after a short amount of time, t gets fairly large. It's not going to take very long for t to get big.
So basically,
For all practical purposes, this is 0.
so basically, the dampening stops the motion.
So without the outside force, the dampening stops the motion. Exactly. So the only real question is, what's going to happen with our non-homogeneous solution? What's our particular solution going to look like? Well, our x sub p, which is usually called in this case x sp, is going to have a cosine omega t and a b sine omega t. SP stands for steady periodic. So the transient solution is your complementary, that one goes away. Your particular solution is your steady periodic. What do we mean by steady periodic? It's going to keep it bouncing and moving in the shape of a what kind of curve? Sine or cosine. And remember, back before when we had a sine of cosine function plus a sine function, we did a whole bunch of fancy trigonometry, and we were able to write that as one function. The book goes through all that same fancy trigonometry in this section, and you can write this in terms of a cosine function, c cosine omega t minus alpha. And I'm not going to go through that whole derivation. It just works out that way. Questions on that? All right, so let's try doing an example and see how these all work out. X double prime plus 25x equals 90 cosine 4t. And the initial conditions are x at 0 equals 0 and x prime at 0 equals 90. What's your complementary solution? C1 cosine 5t plus C2 sine 5t. Why cosine 5t and sine 5t? Where'd the 5t come from? Came from the 25. This would be r squared plus 25. So you'd have r equals plus and minus 5i. So there's your complementary. What's your particular solution going to look like? A cosine 4t. Do I need a b sine 4t? No, not for this one. Why not? Because there's no x prime there. But what I do need to do is take the derivative twice, plug in, figure out the a number. All right, so xp prime is negative 4a cosine 4t. Sine 4t, thank you. Xp double prime is negative 16a cosine 4t. Plug in. Negative 16a cosine 4t plus 25a cosine 4t is 90 cosine 4t. Negative 16 plus 25 is 9a equals 90. So a is 10. So our solution is x equals C1 cosine 5t plus C2 sine 5t plus 10 cosine 4t. Last thing we need to do, take the derivative, plug in our initial conditions, solve for C1 and C2. All right, so x prime is negative 5c1 sine 5t plus 5c2 cosine 5t plus 40 minus 40 sine 4t. Plugging in the first initial condition, x at 0 equals 0, we have 0 equals c1, because cosine of 0 is 1, plus 10, because sine of 0 is 0 and cosine of 0 is 1. But that one's easy to solve. I like that. C1 is negative 10. Plug in the other initial condition. 90 equals, sine of 0 is still 0, so this piece goes away. 5c2, and sine of 0 is 0. That one goes away. 90 divided by 5? 18. Alright, so the solution is x equals negative 10 cosine 5t plus 18 sine 5t plus 10 cosine 4t. Questions on that? Do you think that has the possibility of resonance? Yes or no? How would you tell?
I do.
We have resonance when that number 4 is close to that number 5.
Yeah.
Are 4 and 5 close? No,
They never
typically.
increase. We're going to get any closer to the set.
What I would do, I would go ahead and draw a graph. Negative 10 cosine 5x plus 18 sine 5x plus 10 cosine 4x. I have no idea what my window looks like. Mode. First off, let's put it in degrees. That might help. Radians, I mean. But does it look like you're having resonance?
No.
No. So those 4 and 5, a lot of people would say 4 and 5 are close together. From a mathematician standpoint, 4 and 5 aren't close together.
4.9999.
4.999 and 5 are closer together. Yeah. So it doesn't look like you have resonance. You can see you do get times where you get a stronger vibration and then times when you get a weaker vibration. Sometimes the solutions are working together. Other times they're opposed to each other because the periods are different.
For the most part, there's nothing outside of the norm.
Nothing outside of the norm. No, that doesn't look bad at all. Certainly doesn't look like there's resonance there.